Hello and welcome to SudoKanard. The recent WPF Puzzle Grand Prix was organized by Hungarian authors, including Gyula Slenker, sorry for mispronouncing your name, and it was a high pointer, 99 points, Kropki puzzle, and it was a remarkable construction. And I attempt another solve. I solved it during the contest, but it was definitely on the hard side. So the rule is that you have to put digits from 1 to 8 such that they appear exactly once in each row and each column. Those black dots mean that one digit is double the other, and all black dots are given. And also, in a Kropki puzzle, you generally see white dots, meaning that the digits are consecutive, but here no black dots appear, meaning that you never see two consecutive digits except 1 and 2 separated by a black dot. That's the only occurrence of consecutive digits you can have in this puzzle. So where do we start? One starting point is that a run of 3 digits in a ratio of 1 to 2 must be either 1 to 4 or 2, 4, 8. A consequence of that is that 2 and 4 must appear in those, and the central cell is a 2 or a 4. This is also true here and there. And an interesting point is that when you have 2 digits separated by a black dot, it can be 1, 2, 2, 4, 3, 6, or 4, 8. But as soon as you know that 2 and 4 must appear somewhere here, you can rule out all 3 options for this. So this can only be a 3-6 pair, and that's true for this as well. And in this column, you have 2 and 4 in here, so this must also be a 3-6 pair, and it just revolves around this roundabout. Alright, so those were not true pencil marks, they were there just for the sake of explanation. Something else is that here you don't have 3 and 6, that's true here, but we already knew that. In those cells, we know that we must have 1, 2, 4, or 8. And this is true as well in here. And this is true as well in here, because we can't have 3 and 6 here because of that. This is true in those cells as well. And, well while I solved it on paper, that's it. That's it. I'm showing to the camera. That's the paper on which I solved it during the contest. I didn't pencil mark all those 1, 2, 4s, and 8s. That would have been very difficult to read. Then there's something. On this row, we still have digits here that are either from 1, 2, 4, 8 or from 3, 6. But you can see that those two cells must contain 5 and 7. They are the only cells on this row that are not with a black dot. And perhaps I should use some coloring for those, because they seem to play a very special role. And we can probably also wonder where 3 and 6 go, but I think I'll have a look at this later. So knowing this, it's not that interesting in this case, but we may wonder where 6 goes well, obviously, I've been missing this. This can't be 3 or 6, so these digits are also from 1, 2, 4, 8. And 3 and 6 are in here. But 6 can't be next to 5 or 7. They would be consecutive, so this is 3, 6, and 3. And we finally get some real digits in this puzzle. You can see that neither 5 nor 6 nor 7 can go in here. So 5, 7, and 8 in this column must be in some of those cells. And they must be in some of those cells as well. Some of those cells. And then, where else could we look? We've located a lot already, but perhaps we know that there's another 5 or 7 in here, and another 5 or 7 in here. So I just use the coloring to show. Perhaps I use another color. I use orange. So orange means that one of those two is red for 5 or 7. And then what? So we still need 2 of them in here, 2 of them on this row. I remember focusing on 5s and 7s, and also on 3s and 6s, because we already have quite a number of them in the grid. So I think I use green for 3s and 6s. And I just give up on the coloring of 5s and 7s for the time being, and just use yellow for the cells that can't contain a 3 or a 6. An interesting point is that without a black dot next to a 3 or a 6, you can't have a 3 or a 6. A 6 here would need a black dot here and there. And that's the same here, here, and here. So you see that on this row, the only other place for a 3 or a 6 is here. And obviously, cells that are on pencil marked with 1, 2, 4, or 8 must not contain a 3 or a 6. This column here needs that, this cell for this row, this cell for this column, and we still need one of each in here. But next to the green, I can't have another green because there would have to be a black dot in here, so we get a green cell here, not here, and here. So those are the locations of all 3s and 6s in the grid. So this must be a 6, that's a 3, that's a 6, that's a 3, and it resolves with 6 3 pairs in here. That's a 3, that's a 6. So that's a nice beginning, and I think I just remove the coloring relative to 3s and 6s, and I do some eliminations with the 3s because 3s can't be next to a 2 or a 4. So that can't be a 2 or a 4. This 6, oh, we don't know about those. We still don't know how those resolve. We'll come to this at some point. And the interesting part is that 1 of 8 can't be next to a 1 or 8 with a black dot. So here we have either 1, 2, 4 or 8, 4, 2. So this is 2 or 4. This could be any of those digits. I think that's it, but now Let's go back to 5s and 7s. 5 and 7s can't be next to the 6, so in this column they must be here. Here I can't have 5 or 7, so it must be here. In this column they can't be next to the 6, so they must be here and there. On this row they can't be here. They're not here. They're not here. They must be somewhere in there. So perhaps I should use the coloring. I didn't use it during the contest. But that would seem a legitimate thing to do. Oh, they can't be here. Could be here, could be there. On this row, they can't be here, so they must be here. And this 5 or 7 prevents this from being a 6. That's correct. This 6, well, we already knew this wasn't a 5 or 7. We still need 2 of them in here. Perhaps I should use some coloring to see which cells could still contain a 5 or 7. No, not this one. So all right, on this column, because of those, this can't be 5 or 7. Because of 6, this can't be 5 or 7. So this had to be a 5 or 7. So on this column we have this, on this column we have this or that. Here we still have this or that, and in this column, not this, or we only have 2 options in this column. So that's a 5 or 7. That's 1 as well. We already have 2 in this row. And we still need to put 3 of them in the remaining green cells. That's interesting. And then, so I'm not sure I can deduce anything from that. But there's something I noticed during the contest that I remember, which is, I use orange for that. Let's have a look at those 4 cells. I use some coloring to note that this digit is different from this one, so it's the same as this, and it's different from this one. And the point here is that those 2 digits are a 5-7 pair. And because of the non-consecutive rule, this can't be consecutive with either 5 or 7. So it can't be a 4, a 6, or an 8. It can't be a 3 or a 6. It has to be a 1 or a 2, but 2 wouldn't fit next to the 3. So this is a 1. And I can remove 1 from those, and I can remove 1 from those. But now this row, I know I must have an 8 somewhere here, so it's an 8 with a 4, sorry. This now can't be a 1, so that's a 4-8 pair, and this now becomes a 2, and it gives the 1, the 4. This can't be 1 or 4. This has to be a 4, and this is a 2, this is a 1. This is not 1 and not 4, obviously. And 1 in this column can only be here. That's not wrong. This digit next to this is not in a ratio of 1 to 2, so this is not 4. And this has to be a 4. The counterpart 2 or 8 must be here, and we need a 1 on this row, so it's here. Right. So 2-8 pair here, so this is not 2 or 8, that's 1 or 4. And actually it's not 1, so that's 4. there, that's not a 4. And let's have a look. We need a 4 and an 8 in here. Well, whichever value here just rows some value out from this. 5 makes this a 7, 8 makes this a 5 by the non-consecutive rule. I think I can remove the coloring here. This, well, that's what we call remote pairs in Sudoku, and it was quite tricky to see. The interesting point here is that this is 1, 2, 4, or 8, but those are not in a ratio of 1 to 2. So what happens here is, if we try to put 1, 2, and 4, then this would have to be 8 by elimination, but we would need a black dot. So this is not a 1. So this is 2 or 8, so that has to be a 4. And this is 2 or 8, so that has to be a 1. And now this can't be 2 anymore. So that's 8, that's 2. That's not 4, that's not 4, that's not 1. Because of this one, this is not a 2. And 2 on this row can only be here. That's 8. That's 4, that's 8. And now, because of the non-consecutive rule, that has to be a 5. And that's a 7. And it resolves a lot of the 5, 7 ambiguities. And that's a 5, that's a 7. So we need a 5 and a 2 somewhere here, but that's a 2, so that's 2, that's 5, that's 5, that's 2. This can only be a 4, a 2 to complete the column. We still need 5 and 7 here. We still need a 1 somewhere in here. Not sure where. Here we need a 1 and an 8. But that doesn't work. Did I forget something? Oh, actually I forgot something. So I have actually, oh, sorry about that. Oh, that's not something I usually do. But it so happens that I made a mistake. If you look at this, there was indeed this black dot here that I forgot to put on the Pempa stuff. So now 8 has to go here, that's a 1. And actually, with this black dot, I could have pencil marked the 5s. I could have seen that this was not 5 or... Well, I'm not sure what I could have seen. Anyway, that's a 1, that's a 5 or 7, and that's 8. And this 8 now makes this not a 7. So that's a 5, that's a 7. We solve the remaining 5, 7 pairs, and here this one prevents this from being a 2, so that's 8, that's 2, that's 8, and that's 2. Alright, so there was a mistake in my transcription of the puzzle, but I managed to solve it anyway. Well, that's unfortunate, but you see, I do not cheat. Thanks for watching this video, and thanks to the Hungarian authors for this magnificent Grand Prix round. See you soon on SudoKanard.